Okay, well, let's turn our attention now to the firing patterns of these ventral tegmental area neurons, and that will give us some insight into the nature of the reward signal that we have in the human brain. So what we're looking at here is a raster plot of recordings from the ventral tegmental area, and we're looking at action potentials in a paradigm where an unexpected reward is provided to a behaving animal. So the individual dots that we see down below are individual action potentials on multiple repeats of the same trial. And up above we have what we call a post-stimulus time histogram, which shows us the cumulated firing of this neuron across all of these trials. Now at the arrowhead down below we have the introduction of a reward. Now this is unexpected to the animal, so this is a pleasant surprise, if you will. So with that present surprise, we have a marked increase in the activity of this ventral tegmental area neuron. And so this neuron is now releasing dopamine in the striatum after the presentation of this unexpected reward. And so this is inducing a shift in the activity of the reward circuitry of the orbital and medial prefrontal cortex, which is facilitated by the activation of its thalamocortical connection. So the striatum, the pallidum, disinhibits then the mediodorsal nucleus, and there's some kind of change in the activity patterns in this orbital medial prefrontal network. And presumably, that change, we don't yet understand exactly how this works, but that change is read out in the animal's behavior as the presence of rewarding stimulus. Well, now let's see a different experiment where there's a conditioning stimulus that's present. So the conditioning stimulus is coming to predict the presence of a reward. And after enough trials to reinforce this contingency, what we find is that the firing of the ventral tegmental area neuron now shifts from the reward to the conditioned stimulus. So what this neuron is signaling then is not necessarily the presence of the reward, but rather the prediction of the reward, the anticipation of the reward. So we can imagine why this would be quite important in understanding what happens as people become addicted, be it to a drug, be it to gambling, be it to sex, whatever the experience or the substance of abuse happens to be. Increasingly over time, the firing of the ventral tegmental area neurons, the release of dopamine, and the activation of the reward circuit becomes associated with the conditioned stimulus. Not so much anymore the consumption or the experience of the substance of abuse or the experience of abuse. In fact, if we continue to play this basic paradigm out in time, but now withhold the presence of the reward, what we find is that the ventral tegmental area neuron will continue to fire, at least for some number of repeated blocks of this experiment, when the conditioned stimulus is present, but it actually has a suppression of firing at the time at which the expected reward would have been delivered. But in this experiment, it was withheld. So the firing of this neuron becomes increasingly shifted then from the presentation of the reward to the anticipation of the reward. Now, let's look at a little bit of the molecular biology of what's going on both in this ventral tegmental area neuron, but also in its target, in the medium spiny neuron of the ventral striatum. Now, normally, as you know, there is the integration of inputs in these medium spiny neurons, which are these large neurons here shown in blue. Here to the right, here's the nucleus accumbens medium spiny neuron, and on the left we have a ventral tegmental projection neuron which provides input to this medium spiny neuron in the form of dopamine. So here we see a nice release of dopamine that would be signaling either the presence or the prediction of a reward. Now this medium spiny neuron is also integrating inputs that are derived from the cerebral cortex, as well as structures like the amygdala and the hippocampus that are providing input here. We haven't talked a lot about this, but the dopamine neurons in the midbrain are also getting input from widespread regions of the cerebral cortex and probably lots of other structures in the brainstem as well. Now, what's meant to be depicted here in this slide is really, I think, a remarkable feature of the neuropharmacology of this system, and that is at just about every dendrite that's relevant in this circuitry, there are receptors expressed for virtually all known drugs of abuse that human cultures have ever discovered. And indeed, some of these receptors are even found on the presynaptic terminals that provide input to these cells. So, for example, in the nucleus accumbens, we have receptors that can interact with substances like cocaine and amphetamine, which can act to increase the presence of dopamine in the synaptic cleft of these medium spiny neurons. We have receptors for phencyclidine, for opiates, for the cannabinoids, all expressed on the synaptic junctions of these neurons with their inputs from the telencephalon or from the dopamine inputs derived from the ventral tegmental area. And in the VTA itself, we have opportunity for substances of abuse to modify the way these VTA neurons either respond to local GABAergic interneurons or from their cortical projections that are releasing glutamate. So the upshot here is that the brain's intrinsic reward system is expressing receptors that can interact with a variety of exogenous compounds that we can consume and can co-opt the function of this reward circuitry. So let's look at what happens following addiction in this system. So the details here are a little bit beyond our scope, I think, so we won't have to focus on them, but I do want to give you a sense of the physiology of what's happening here. So when this system becomes addicted, what we find are molecular changes within the neurons of the ventral tegmental area and the nucleus accumbens. There's plasticity of synaptic connections. There's very likely structural change in the distribution of synaptic terminals and the structure and distribution of the dendritic arbors as well. But from a physiological standpoint, the key feature here of this addicted circuitry is that there is a reduction in the ongoing release of dopamine that is normally reflecting the nuances of everyday life. That is, those momentary pleasures that we all experience from pleasant social relations, perhaps a kind word or a gentle touch, or the sound of our favorite song that we might happen to listen to on the radio or in our music player. All of these nuances of daily life that give us some sense of pleasure and reward are associated with the release of dopamine in the circuitry. It's exactly these nuanced rewards of everyday living that become diminished in the addicted circuitry. What we find in the addicted brain is that the release of dopamine is increasingly tied to the prediction of consuming the substance of abuse or experiencing the situation that is intended to provide for that reward. But as we saw in the neurophysiological experiments, it seems as though the release of dopamine is increasingly tied to the conditioned stimuli, not the actual consumption of the abusive substance itself. So what we see then in this circuitry is that the release of dopamine as well as the phasic stimulation of this circuitry that's coming from cortical systems, is increasingly tied to these conditioned stimuli. So I think this is providing great insight to understanding addiction and addictive behavior. Perhaps this is why the presence of, let's say, drug paraphernalia, or the presence of acquaintances and other individuals that might otherwise be associated with abusing drugs, can have such a powerful grip on the addicted individual, because these are conditioned stimuli that are predicting the consumption of a substance of abuse. And in the presence of these conditioned stimuli, we imagine that these ventral tegmental area neurons might start increasing their firing, releasing dopamine, and predicting the consumption of the rewarding stimulus. But if the brain of the addict is anything like the animal model data that I just showed you, we can expect that the actual consumption of that abusive substance is no longer producing a release of dopamine. If anything, there might be a withdrawal of dopamine that would happen at that time. So addiction is a serious problem. It's not necessarily an intractable problem, but for sure we need to develop better methods based on neuroscience discovery for the treatment of this human condition. Well, I hope this has given you some insight as to what might be going on in your own brain when you have a rewarding stimulus. And if you do believe that you are at risk for addiction, I would urge you to seek counsel, perhaps seek medical intervention if that's appropriate. But otherwise, I think it's important for us to understand how this part of our brain works. Certainly any of us that are in a privileged position that might have means and access, it's critical for our health, for our wellness, for the health of our families and our relations, that we be on guard and that we protect ourselves, even this aspect of our behavioral health, based on what we're learning about the brain and its intrinsic systems of reward. Well, thank you for your attention. I hope I wasn't a bit too heavy-handed with you on this topic. I'm used to talking to medical students about this particular system, and at least in the medical profession, the temptations are very real. And the abuse of substances among the medical profession is certainly a problem that we have here in the United States and in many other places in the world as well. So knowing more about how the brain deals with reward and how the brain can so easily be co-opted by substances and experiences of abuse gives us better information that will allow us, I trust, to develop better strategies for maintaining the health of our brains, the health of our bodies, and the health of our social relations. Well, I'll see you next time as I wrap up with you our experiences in medical neuroscience.